Today we're gonna go check out this fault right on the other side of the hill over here. There's a big fault that goes for more than 50 kilometers, and there's rocks on either side of it that we can match up to get an idea of what the fault has done over the last 12 million years. So we're gonna look at some rocks in the northern part of the range tomorrow, but today we're going down to the southern part. So that's the plan for today.
Continental deformation is generally the result of the relative motions of the Earth's tectonic plates, and the Basin and Range is a really good example of that. Over the last 30 million years, the Pacific plate has been moving roughly north-northwest relative to the North American plate at about 5 centimeters per year total. Now, about 3 centimeters per year of that is being accommodated on the San Andreas fault zone, but a fraction of the plate deformation is distributed hundreds of kilometers into the North American plate and occurs as a very complicated system of faults that comprise the Basin and Range province. The theory of plate tectonics tells us with great accuracy how the relatively few plates that exist on the Earth's surface are moving with respect to one another, and it tells us those motions very precisely. What it doesn't predict is when the zone gets very wide and complicated, how individual pieces should be moving in order to get the job done of having one plate move past another. And so the thing we're trying to accomplish here is to reconstruct fault block by fault block all of the pieces that exist within the Western North American plate boundary zone, so that we can generate a model of how the deformation took place over time.
The reason we wanted to make a model is we wanted to compile all the information that exists into one centralized format that would allow us to evaluate the data with respect to each other. So you can have a geologic story that's tight, that's contained, that makes sense in a given region. But do these different geologic stories of how faults are moving, the rate at which they're moving, the time window over which they move, can they be correlated to each other? Do they make sense? And so to do this, what we've been doing is gathering geologic data. Most of it has been collected and published and analyzed and reanalyzed over the last 50, 60, 70 years on faults, their magnitude, direction, and timing of motion, and compiling it into one model of how the Western US is deforming over a given window of time. So this is the time bar going from 36 million years ago to present. And so if we jump back in time, you'll see this black bar descend and track the time over which this deformation is happening. As we start the model, you can see here that extension first happens in the northern Basin and Range. Then the southern Basin and Range starts to pull out ranges from underneath the Colorado Plateau. And the central Basin Range here is late in the game, in the last 15 million years to present. I don't know if we'll ever know exactly if the model is correct. I think that there's aspects of the model that can be shown to be more correct than others, such as if there's something that I put into the model that's not supported by geological data, there is a chance I could go out and find the critical piece of geological data that will show that that aspect of the model does match the data.
So Brian and Nadine have made this model of the Western US, how it has deformed over the last 35 million years. And that predicts for this area that we have a fault that has 20 to 30 kilometers of displacement. But there's no evidence that supported that. And that kind of motivated us to go here and look for anything we might find across the fault that we could correlate. Across, just like in that big valley, is where the fault lies. And we think there's been 20 kilometers of offset along it. that the rocks we see here match up with rocks 20 kilometers to the north. It's beautiful out here. These are kind of cool.
So these are the rounded clasts
Yeah,
that you're talking about.
I think these were deposited in a river maybe 20 million years ago. And that river since got broken up by the fault.
Basalt with large plagioclase crystals in it. Theoretically, each river carries its own sort of suite of rocks and clasts, so it kind of has its own fingerprint. So the idea would be to try to get a very good detailed idea of the type of rocks that were being transported by this river that was here, we think about, I don't know, 20 million years ago or so. Take them back to the lab, cut them up into very, very thin sections, and look at those really thinly sliced pieces of rock underneath a microscope, and then try to compare that with the rocks over in a different mountain range. If they're identical, then we can pretty much say that it was the same river that crossed this area, and that since that time, the fault has moved the deposits apart. If they're different, then we're left looking for other pieces of evidence.
So this data serves as a test. The model's predicting that we should have about around 20 to 30 kilometers of slip of offset on this fault, and but we just haven't found that yet. But we think this is the holy grail that shows us that this fault did accommodate 20 kilometers or more of offset.
I don't think the model will ever be done. I think it will continue to get more and more refined as scientists use it to try to figure out what can be improved.
Doing field work in the mountains here is fantastic. You walk through hundreds of millions of years of Earth history over just a few footsteps. And then you see rocks also being fractured and broken apart as faults dissect the landscape and create new valleys and new mountains.